All right, so today we are again nearing closer and closer to the end of this course. We're looking at the definite integral today, its definition, how we use its notation. It's again some new notation, like some notation. It's a little bit simpler, I think, but still requires a bit of thought. We're going to talk about the properties of integration, just like we had properties of differentiation. There are things that help make life easier, and so we definitely want to look at those. We're going to use them in the context of area problems, how they relate to the area problems we've already done, and how to compute them numerically. All right, so let's jump right in. Okay, so first of all, what is the definite integral? Well, we should be familiar a bit with this notation over here. Well, particularly with this notation over here, right? What is this? This is the Riemann sums, right? R sub n from previously. And these were the sum of the rectangles to try to get an idea of the accumulation under the curve, right? We'd either take from the left or from the right, or we might have looked at midpoint formulas or other types of sums. But the idea is the same, that you're grabbing one point on the curve and using a box to try to get a sense of what the total area under it is. Because if it's a velocity curve, then you're getting the total distance. If it's a rate of flow, you're getting the total amount of volume, things like that. So this is the Riemann sum. So the definite integral, what we've defined it to be, is the infinite limit of that. So take now infinitely many rectangles. And what do we get? If we go to the limit, what is this approaching? Well, it's approaching the exact area under the curve, right? And so that in particular, instead of having all this crazy notation on the right, we call it its own thing, just like we did with the derivative. We don't need the limit notation for the derivative, so we don't need it for the definite integral. And this is all that it means. And so I have this little diagram under it to tell you what this notation really represents. Um, Here, this big S is kind of like the continuous version of the sum for sigma. So this big S you can think of as sum or integrate or put all together. The lower limit of integration, you can also call this the start. The upper limit of integration, you can call this the stop. Right? This is really for some, interval on A to B. So instead of doing those tiny subdivisions by hand, we just say started here, ended here. Right in here, this is the function to be integrated. So this would be your velocity if we were looking for total displacement. And then here, this piece really just means with respect to what variable. Eventually, this will become important, but you should know that this is really just a piece of the operation. This part in here is what's being integrated, and all of this information that kind of surrounds it is the operation of integration. All right, and it tells you start, stop, and what direction you're summing. We're summing along the x-axis is what this says. Okay, so we call this the integral of f from a to b. And it's the same way of saying, sum up all these rectangles under this curve, but we're going to do so infinitely fast, infinitely thin rectangles that will take us to the exact area. So again, what's on the left here is supposed to be nice and simpler and represent all the information that's on the right. So with this limiting process, we have to ask ourselves what functions fit the bill to be called integrable, meaning we are able to integrate. So integrable functions means, in a nutshell, they're continuous and or they have finitely many discontinuities, all right? Meaning that you could count them. If there's infinitely many discontinuities, that doesn't fit the bill. We can't really integrate where that function has those problems. But if there's a finite number of discontinuities, we can just kind of work around those. We can break up the integral to dodge those problems. Okay, because the reason why is because if it has a discontinuity, let's say like a hole or something like this, or a jump, if we're shading in infinitely thin, we can just say, well, we're not going to miss any area under there because these rectangles are super tiny, and then we'll just pick up and keep going, right? And so that won't be a problem in the context of the whole area under the curve, okay? Or this idea of accumulation. Little hiccups are not a big deal. A ton of hiccups, a very big deal. So that's what we call integrable. So you have to make sure that you can, if you're working with a function, that it fits this description. Most of the functions we play with will fit this description. Okay. So the properties of definite integration, similar to the properties of differentiation. There are things that help us rewrite them, manipulate them, solve problems in different ways. The first one's probably the most different from differentiation. I don't think there's a perfect analog here, but the idea is that if you reverse the order of integration, meaning going from B to A instead of A to B, it's the opposite of the integral. It's the opposite of that value with those limits flipped. Meaning, if you go ahead and, let me do this with green first, keep the color coordination here. If you integrate here and you go from B to A backwards, and you're, gathering some amount of accumulation under here, going this direction. If I flip the order of integration and I'm going this way, it's going to negate that accumulation. But I think that this is honestly the wrong way to state this equality. Maybe a better way would be to say this. If we put it in the context of the velocity problem, right? You got some particle, and this is your velocity function. We know from here, from A to B, the area under here is equal to what? This area is equal to the distance traveled, right? The total displacement. And this is equal to the integral from A to B of v of t dt. Remember, velocity is signed and it has a direction, so positive velocity means that it's moving in a positive direction. So if we go this way from A to B and we integrate the velocity, we'll get all the accumulation in that positive direction. If we flip it around and then go from B instead to A, well, then we're going to need to negate that to account for the fact that we're going in the wrong direction, right? And we'd be accumulating negative displacement. Okay, so I hope that's clear. Just the idea is if you change the direction, you're negating the whole integral. Okay, so second up, we have this idea. Let me box this off here. This is all for part one. This idea for number two, which is that the integral from A to A of a function is 0. Meaning, if I start and stop in the same place, that means I will accumulate no area, right? Because these are infinitely small. So this should be pretty straightforward to understand, that since we're doing pencil shaving thin, rectangles, they're in the limit, that the limit of those individual rectangles is going to 0. Okay. And so then for number 3, a scalar constant k can be pulled out of the integral, right? So an example of this would be, let's say I have the integral of 5/7 x squared dx from 1 to 3. And you might be thinking to yourself, I really don't want to deal with this 5/7 because it's not a part of the problem. So you can pull that scalar out and then just be left to work with the integrand rather, which is this function inside. Okay, this only works for scalars. I can't pull variables out of the function because they're being integrated, they're being operated on. But that's an example of that. Number 4 is that you can split integration over sums and differences. Okay, so if I have an example of, let's say here, like from, again, 1 to 3, and I had instead x squared plus 3x dx, I can instead break this up into the integral of x squared dx and the integral of 3x dx. Okay, so very similar to differentiation. It works nicely over what we call linear combinations. So again, scaling like this and sums and differences like this, they're preserved. We can break them apart and deal with them separately. And that's often very, very, very helpful, um, especially because integration is a little bit more complicated. So those are nice properties of it. There are also a couple others that are worth noting, and I have these nice graphs that I pulled from another text, actually. And so it illustrates the points here. So here's the zero width interval. There's no area under a single point. The constant multiple idea is that you're really just scaling the area, so that can be preserved pretty easily by just pulling out that constant. The sum of areas property, why we can split it. Right, here's your f, here's your g. If f was a constant, we're really just adding this to g, and so it's just up a little higher. It's going to be the same amount of area if we were to just add those. Here, this one is also good for the additivity of definite integrals. The fact that you can start and stop. We didn't do this one up here, I don't think. No, we did not. So the fact that you can start and stop. So if you have some integral from a to c, and you want to break it up and say, well, I want to look at first the integral from a to b and then from b to c, you can do that. Those are equal, right? Like there's nothing stopping 2 plus 2 equaling 4. Same with 1 plus 3 equals 4. It's the same thing. You can slice this up however you want, and they will add up to be the same grand total. And then these last two are a little bit more nuanced, and their applications are for probably like harder approximation problems when we're really just trying to get a handle on what's going on. The fact that an integral, this one got broken between two lines here. The fact that an integral, all right, will be stuck between, well, b minus a, this length is, or this value is this length, right? B minus a, just the difference between those two. So this right here is the length b minus a. And so what it's saying is the integral's value will be between the smallest value f takes on times the length of the interval and the maximum value f takes on and times the length of the interval. And you can see just from a geometric argument why that makes sense. Okay, if it doesn't go any lower than this, right, then this is where we can cut off that box, etc. And then here for domination, again, domination meaning that one function is always higher than the other throughout an interval. We'd say f of x dominates g of x on a to b. That means that it is going to have a higher definite integral than g of x from the same start and end point. Okay, so these are kind of the key properties of integrals. And again, in order to be able to even talk about these things, you need to make sure your function is integrable on that interval. All right, so I'm going to do an example most of the way through. I'm actually not going to do absolutely everything here, but we're going to compute this definite integral three ways, just so you kind of see the different perspectives on it. The first is we're going to approximate it with Riemann sums. And so, you know, what this would look like, let's say with Riemann sums, and we'll say with n equals 4 subdivisions. All right, so again, looking at this function, we have, you know, this is my integrand. Here are my limits of integration, upper and lower, and this is the variable that I'm integrating with respect to. So, you know, what does this mean in Riemann sums perspective? Well, actually, let me draw a better set of axes because of where we're at. So we're starting at -4 and going to 0. So on my axes, I'm going to start at -4 and head on into 0. And so what does this look like graphically? Well, I know what this curve looks like in my mind. I will maybe try to leave it a bit of a surprise. We know it does something like this. Actually comes around the rest of the way like that. But we're only caring about from -4 to 0. So this is our f of x, our integrand. All right. So we're trying to approximate this integral, which we know is the signed area under this curve, the limit of the Riemann sums. We're going to approximate it with the Riemann sum with n equals 4. And we'll do let's do a right-hand sum here. Okay, and so a right-hand sum, splitting this into 4 subdivisions, would look something like this. So here's 1, 2, 3, 4. We know my delta x is a width of 1. And then we're going to go ahead, and since we're on the right-hand sum, we're going to grab the heights at the right-hand side of each of these. So really, we're going to have, delta x times f of -3 plus f of -2 plus f of -1 plus f of 0. And so this right-hand sum we know is 1 times, well, f of -3 is really radical 16 minus 9, right? Plus f of -2 is the square root of 16 minus 4. Plus square root of 16 minus 1. Plus the square root of 16 minus 0. Now I had this in brackets. I'm just going to drop that and do it like this. And so, you can simplify this as much as you'd like. It's not going to be great. Right, this will be 4 here. But we'll go to our calculator and get an idea here. All right, and after punching that in, we'll get it's around 13.983. All right, so this is our best guess for this area. We'll say this is approximation number 1 with our right-hand sum for this area under here. All right, now we can do this also with technology, and technology does a much better job than we do. It actually uses something that's a little bit more sophisticated, which you'll actually learn in Calc 2. It's called Simpson's rule. It's a derivation of that. But what you can do is enter this into your calculator with this information where you know we're starting at -4 to 0. Our integrand is 16 minus x squared dx. So again, it might look slightly different on what you're using. This is like an emulator here. We're using fn int. That I did that too fast. Fn int. It's usually math 9. And it will, on the 84s, it'll give you this menu where you can really just put in your values in the notation. If it's an older one, you just have to do it in order. And you can just do a quick Google of it. Use the word syntax. And then, TI-84 and look up what you're trying to type in, and it'll give you that. But here, we're doing the square root of 16 minus x squared dx. You have to tell it what you're integrating across. And then we'll see after that our numerical approximation is 12.566. And what this is really doing is doing what you would do by hand, but way faster and way more accurately. The problem with it is that you can break it, right? If you use very, very tiny values and use a lot of those, you're going to start to get truncation errors and memory issues. So the functions do have to be pretty reasonable. And your scale has to be reasonable. So consider what you're working on always. But here, this is not so crazy. So this is actually closer than I thought it would be, but there is still a significant difference between 4 rectangles and, however many hundreds or thousands of rectangles that your calculator is using, but it's still not doing it exactly. Okay. We know the meaning of the definite integral is the limit of this process, and the limit of this process is exact, and it's where it's going if it does converge. And this really should converge. And the reason that it really should converge is because this function is really a semicircle of radius 4. Right? That's what this equation is. And since it's a semicircle of radius 4, we know the whole picture would be a full circle. What a perfectly drawn circle that is. And we know the area of a circle is pi r squared. And so that's for the full circle. That area would be pi times 4 squared, which is 16 pi. But we also know that we're only taking 1/4 of this for our actual integral, right along here. And what is that? Let's call this, A1. This is 16 pi times 1/4, right? Just by the rules of symmetry. And so this is really 4 pi. And what is 4 pi? Well, 4 pi is 12.5637061. So that's pretty darn good. Okay. Pretty darn good. But here we have it written exactly. We don't need to move to a decimal approximation at all. So we know exactly via geometry. We don't need to use the approximation symbol anymore. We can say this is 4 pi. Again, the more precise we can be, the less computation we need to do, and the more degrees of accuracy we have for later on. Okay. So again, what did we just do here? We tied together the notation of what the problem's asking for, getting the signed area under the curve. I keep saying signed area because we do need to consider, is it above or below the x-axis? Riemann sums being an approximation for that. We get a way better approximation using the calculator because it can do more grunt work than we can. And the idea that it's tied to area so that you can compute this geometrically whenever you have the chance. You're not always going to, but sometimes you can. All right. So here, quickly, I'll walk you through how we'd tackle a problem like this. Maybe you're given a graph and you're asked to compute this definite integral where the function is graphed below. We don't have the formula, but we do have the graph, and that's okay. So how we would do this is, first of all, notice that you can split this up. Since you can split up integrals, you can chop it up where you have nice and easy ways to compute the area. And you also use symmetry to your advantage. So, you could break this up into, this is A1, this is A2. Here's a triangle, I can compute that. There's A3. Here's a square, that'd be A4. Here's another triangle, A5. And here's a half circle, there'd be A6. So I have kind of 6 regions I could play with. All right, so let's maybe grab all the positive area. Okay, all the movement in the positive direction if this was velocity, right? All the positive displacement. So this would be, A1 plus A2 plus A6 would be all of that. And so, we calculate that area. This is a height of 1 up here. So we know A1 is really, it's 1 by 1, and we divide it by 2. So that's really, oops, why am I saying equals here? So this is really equal to 0.5 for A1 plus A2. This is a quarter of a circle of radius 1. So that'd be pi over 4. Plus A6 is a semicircle, so that'd really be pi times 1 over 2, because we're cutting that in half. Okay. So if we could simplify this a little bit, we could just say this is 1/2 plus 3/4 pi, maybe for that positive bit. And then for the negative area, the negative displacement, we're looking at A3 plus A4 plus A5. That's all the movement in the negative direction. And so we already kind of did the work on how big a triangle this size really is. I know I've got 1/2 plus 1/2 for A3 and A5. Those both have the same area. And then A4 is just a box of width and height 1. So that's really an area of 1. So this is all 2 together. So I have my positive area is this. My negative accumulation, my negative area is here. And so the whole integral from -3 to 4 of g of x dx is equal to this positive displacement. It's the net, right? Minus 2. And so, all that together, 1/2 minus 2 is -3/2 plus 3/4 pi. And we can leave this in exact form since it's geometrical. But again, here we're leaning on the fact we don't need to draw rectangles in here. We don't need to approximate this because we know that the definite integral is the limit of those r sub n's. Meaning, and that limit is the exact signed area. So we are instead here giving what we're handed, which is some pretty easy to compute areas, and doing the work of accumulation that way. Okay. Now, there's also some more creative ways you could have gone through this. If you split this up and said, well, I see, I've got a triangle right here that's positive and a triangle right here that's negative. You can just say, these cancel each other out. This was like moving forward and backward the same amount. So then you kind of save yourself some work. That's probably the only real simplification you can do here. Everything else was, easy enough. But in general, if you see symmetry, you see things that can simplify that problem, you are welcome to use it. You're leaning on geometry here. All right, and lastly is just a quick application that's often given because it's kind of so easy once you have your head wrapped around what the integral really means. This is really that signed area, the accumulation of the velocity, the accumulation of the change gives you kind of this net change idea, the area under the curve. If you're looking for the average value, though, of a function, average is a very hard thing to compute when the function is continuous, right? It's easy when there are test scores like 95, 87, 36, right? Those are discrete values that you can weight. And how would I do that? Let's say I had 5 test scores. I got a 95, I got an 87, I got an 85, I got 100, and I got a another 87. My average test score, what would you do? Well, you'd take all those outputs and you divide it by the number of inputs, which is 5. So that's the average. You can't do that when you have infinitely many numbers between 0 and 1, right, on the real line. Between A and B, there's infinitely many numbers. So how do you get a sense for how many inputs there were? Well, that's how you get the average value. You use integration. You accumulate all those outputs from A to B, and then you divide by the length of the interval. And in so doing, you are now averaging out that whole value of f. It's kind of like a weighted average. And you will end up with that average height of the function over the whole interval. Okay, so as an example, the average value of, let's just say, let's say for a falling object, 9.81 t squared dt from, let's say, from 3 seconds to 6 seconds. All right, so this would be maybe the total change in velocity, since this is our This is our acceleration function, right, due to gravity. So what you could get here is, I wrote this up wrong. We'd really be looking at, a of t. The average value of this function from t equals 3 to t equals 6, maybe trying to get the average value. So we'd get the average acceleration really over this interval. And so how we would do that would be to take the interval from 3 to 6, 9.81 t squared dt, and then divide it by the length of the interval, 6 minus 3. Okay. So again, I feel like I kind of botched that by giving the wrong notation at the beginning. So just to recap, if I wanted to find the average value of the acceleration function from t equals 3 to t equals 6, the average value of the acceleration in this time interval, you divide it by the length of the interval and then integrate that function. This can be done with your calculator, and so can this, right? You're multiplying it by a third. So let's do that quickly. So you'll see on the left, we calculate this integral. This would be 618.03 times a third, which I guess we should have an approximation sign here, which is equal to 206.01. Okay, and this would be meters per second squared if it really was acceleration. All right. So this is how you can get the average value of a function over an interval. All you need to do is add up all those values along that length and then divide by the length of time or the length of the interval, etc. Okay. So that's just a neat application, and it has as many contexts as functions do in general. So finding the average value should be a helpful thing to have in your back pocket. But that's not really the key of today's lesson. The key of today's lesson was to learn about the definition and its notation, its properties and what makes something integrable, how it's connected to area, and how we can do this numerically and geometrically, get an interpretation of this. And this will help us with our last topic, which is the fundamental theorem of calculus. And that's coming to you next time.